Good morning again. This first panel will focus on the technical and scientific aspects of autonomous and connected vehicle technologies. First, I'll start with an overview of those technologies and their deployment. My background, just to give you an idea, is on traffic engineering, my expertise in traffic flow theory, and civil engineering. Dr. Carl Crane is a professor of mechanical engineering at UF. He's been working on autonomous vehicles for several decades. He's developed both surface and water vehicles, autonomous vehicles, and he'll discuss the technology and sensors for autonomous vehicles along with the deployment challenges. Next, Dr. Shailene Klassen is a professor and chair of occupational therapy, and she's an expert on fitness to drive issues and driving simulators, and she'll discuss the interactions of technologies with humans, and particularly perceptions by older drivers. Dr. Sanjay Ranka is a professor of computer and information sciences and engineering. He's an expert in parallel computing and machine learning, and he'll discuss transportation-related data management applications that are underway. First, let's start with the status of the transportation system in the U.S. And Ken mentioned the more than 40,000 fatalities in the U.S. This past year. This graph shows how the number of fatalities have changed since 1975, along with the fatality rate per 100 million VMT. As you can see, both numbers have been going down, and even though vehicles and the infrastructure have generally become safer, the vast majority of these crashes, 94%, are due to human error. So the promise of autonomy is to reduce these substantially or even eliminate them. You have seen various tests by Google, Uber in the news, and now there are more than 1,400 vehicles being tested by more than 80 companies across the US. We see more and more shuttles, such as the one shown here on the screen, which is the one in Gainesville. And I'm going to play a little video here. So as you can see, the vehicle is going really slowly. It's really frustrating if you're behind it, but it is because it's mapping the route. During that time, I don't know if you caught that, but there was a bicyclist zooming by, and the vehicle just stopped. Wouldn't it be nice if all our vehicles could do that? And this, by the way, was not staged. This is something that just happened while the vehicle was mapping the route. This shuttle is going to be part of the regional transit service in Gainesville. We're waiting for approval from NHTSA. The vehicles themselves are in Gainesville, but we hope this will give us great information about interactions with the public, how people might use autonomous shuttles. Now, let me take you back to when vehicles were first invented. That's what they looked like. So we didn't get to where we are overnight. It took about more than 100 years to get to the transportation system of today. And at that time, acceptance of vehicles was very far from universal. There was significant congestion, significant safety issues, no rules of the road, no stop signs, no traffic lights. And at the time, of course, horses were prevalent with problems, manure, mistreatment of the animals, and so on. So mixing the two was a challenge. The horses were getting scared of the cars. So this little invention was introduced. It's a horse head so that horses wouldn't be spooked. Of course, that didn't work. But in some ways, we face similar issues today with humans accepting autonomy. How will conventional vehicles and drivers operate around autonomous vehicles? Will they cut them off because they can trust that an autonomous vehicle will stop? How will the autonomous vehicle interact with pedestrians and bicycles and scooters, which are very prevalent on the UF campus? So the concept on this slide is kind of similar to the horse head. Now we want to make the vehicle look and act like a human driver, so that pedestrians and other human drivers can understand what the intent of the vehicle is. So if the vehicle is approaching, are they going to stop for me to cross if I'm a pedestrian? And the autonomous vehicle logic also wants to know, is the pedestrian standing on the side of the road getting ready to cross, or are they just waiting for something else? So in my field, in traffic engineering, we use this graph in introductory transportation engineering courses. And it shows the three major elements of the transportation system: the vehicle and its characteristics, the driver, the traveler, and then the infrastructure and the environment. So each of these affects and is affected by the other elements, and altogether contribute to the performance of the transportation system. So the speeds that we observe are a product of all these. The capacities are a product of all these. So as an example, when you have a heavy truck, it's traveling much slower when you have a steep upgrade. So the combination of the vehicle characteristics and the infrastructure result in a particular performance. Each of us as humans, we react differently to the different designs. Some of us are more conscious, some are more aggressive, some we want to keep longer distances, shorter distances. So this variation that we have from human drivers also affect the speeds, the travel times, and the safety. So how do the EVs fit within this system? How will different travelers use and interact with AVs, with autonomous vehicles? How will different vehicles from different manufacturers operate under different highway designs? So when we're introducing autonomous vehicles, we have to consider all three elements. We have to consider the variabilities in driver behavior, both in using a particular autonomous vehicle and driving, as well as interacting with it as a pedestrian or as a bicyclist. So here's a graphic that is of this type that is commonly used to describe autonomous vehicle operation. So an autonomous vehicle maps the terrain. It has several types of sensors by which they're able to look at obstacles and navigate through the highway network. Now, once these are detected with the vehicle sensors, then the vehicle's logic decides how it's going to move, whether to stop, and whether to change lanes. But imagine this scenario on this slide where you have an autonomous vehicle which approaches a crosswalk, and there's a pedestrian already on the crosswalk. There's a bicyclist further ahead, and this can be seen by the sensors. But there's another pedestrian standing there, and its view may be somewhat obstructed by the sensors on the vehicle. So can the vehicle detect the pedestrian, first of all? And even if it can detect it, can they determine the intent, whether the pedestrian is getting ready to cross? When we have a human driver, the human driver can communicate that nonverbal with the pedestrian, determine the intent, allow them to motion them to pass, and so on. And this becomes a very difficult problem, especially considering the variability in driver behavior. So different individuals will behave very differently. Now imagine this environment, freeway congestion, and an autonomous vehicle operating in it. In this environment, you'd have very frequent lane changing as vehicles are trying to get to the correct lane for their destination. And so when you have an autonomous vehicle under this environment, the autonomous vehicle has to recognize the intent of other vehicles changing lanes. Second, you have a distance that an autonomous vehicle needs to keep with a vehicle ahead to maximize its safety. If that distance becomes too long, then the space that this queue occupies with conventional vehicles becomes much longer. If it's too short, it may cause rear-end crashes. So the vast majority of autonomous vehicle crashes that have been recorded so far are due to human error of a vehicle crashing, of a conventional vehicle crashing into an autonomous vehicle, because they don't react quickly enough. The human driver doesn't react as quickly as the autonomous vehicle. So autonomous vehicles do have the potential to significantly improve safety and mobility, but there are risks in their deployment. Those deployments may be derailed if we start increasing delays and crashes. So the wrong type of deployment, when the technology is not ready or well thought out, will backfire. Let me show you now an example of how we're approaching this problem to avoid these pitfalls for deployment of autonomous connected vehicles. We have a partnership at the University of Florida with the Florida Department of Transportation and the city of Gainesville to build the iStreet, which is a real-world test bed. And its objective is to test, deploy, evaluate several different advanced transportation technologies. Gainesville and the UF campus where this is deployed are ideal for this type of testing because there's significant pedestrian, bicyclist traffic, there's scooters. We have an extensive transit network. We have relatively low speeds and good weather. Also, Florida is very welcoming to autonomous and connected vehicles. So the Florida Department of Transportation has funded the deployment of communication devices for connectivity along several corridors, including corridors around the UF campus. And those allow vehicles that are instrumented to communicate with infrastructure. So what I'm showing in this slide is a system we're developing for optimizing signal control, so the operations of traffic lights, and the way that the green is allocated to the traffic approaching the intersection, while at the same time advising arriving vehicles that are able to receive this information what their optimal path is or their trajectory. So the autonomous vehicles approaching the intersection, as soon as they reach the communication range, they receive very specific information on the path that they should follow, and they can execute it. We've been doing experiments now for a couple of years, and we've developed the hardware and software to be able to do this. With connected vehicles, which are also part of the mix, if they have the ability for connectivity, then they can also receive information on optimal speeds. And right now we're working on an app where we are able to have even conventional vehicles with no connectivity be able to receive information on optimal paths, advisory speeds in essence. This video shows how we use radar and other sensors. This is at an intersection on the UF campus, Stadium Road and Gay Lemrant. You see our football stadium there on the left. So that intersection is instrumented so that when the vehicle is connected, it can receive an optimal path, which is the green points there. So when we first detect a conventional vehicle, we estimate its projected path, we optimize signal control, and then as the vehicle moves, we reevaluate that path and adjust the signalization if the vehicle is slower or faster than what we predicted. So with initial simulation experiments for a fully autonomous simulation environment, but with communication, with the infrastructure. Our experiments show that we can reduce delay by 20 to 70%, depending on the demand. Of course, that number goes down when you have mixed traffic and lower market penetrations. We start to see a significant difference when we get to about 20% market penetration. So a system like this cannot function if it doesn't have communication with the infrastructure. And to be able to take advantage of such systems, we have to have collaboration that involves the public sector and industry, academia. And so iStreet is approaching this as a collaboration with our partners, FDOT and the city of Gainesville. Because if we don't get this right, if we don't make a difference, then congestion will get worse, and deployments for autonomous vehicles will backfire. So this map here on the right shows our ongoing deployments around Gainesville for iStreet. So I invite you to check out our work on iStreet. You'll hear some more with the next 3 presentations, and we look forward to working with you to improve mobility and safety. Thank you. And with that, I'm going to get Dr. Crane here for the next presentation.
Okay, well, thank you very much. Oh, we call her Dr. Lily. So she's a fantastic leader of our efforts down in Florida. So I was asked to try to do this. I'm watching that clock there. A 15-minute overview of autonomous vehicle technologies to a group of experts in a wide variety of topic areas, which is usually a recipe for disaster. So here goes. A little bit of the I'm glad you started with the old cars, and I hadn't seen the horse head. I thought that was great. Background, I've been in Florida a long time. I'd been in the Army before I got to Florida, and like in the Army, every 3 years you transfer, and so my 3 years got up, I was like ready to wear it, and I've been there now for like 35 years, so I guess it's not gonna happen. But over that time, we've done a lot of autonomous vehicle work for the Air Force, for different projects that they had. And then in the mid-2000s, DARPA had their Grand Challenges and the Urban Challenge. So I was going to say we participated in all three. The Urban Challenge, the Grand Challenge, if you're not familiar, was they gave along a desert route a bunch of latitude, longitude of a whole bunch of points, about a 150-mile long path. And whoever could do it the fastest would get $1 million, well, then they upped it to $2 million prize. And the first year, 5 vehicles got about 5 miles, and 5 got about a mile, and 5 self-destructed at the starting gate. And they were the best 15 out of 43. We were in the middle group. We got about a mile. My goal, make sure we get out of sight of the starting gate, and then whatever happens, happens. The second year, though, definitely, it was about a year and a half later, they redid it. And again, 43 teams. They put 23 in the race. 5 completed, and the fastest was Stanford. And they got the $2 million prize and kind of led off to Google Waymo and all that. We got about 14 miles and our GPS went out. Well, our GPS, which is supposed to broadcast corrections of a few centimeter level accuracy, had an 8-meter error in GPS. And the entire vehicle was a single point failure vehicle. So I can't say that I was disappointed. That's not the right word. That was actually our high water mark, I think. And it was really exciting to see that happen. So now I've used up all that time on the first slide. What I want to do today is just show sort of a basic overview of what's going on with autonomous vehicles. And I don't have to spend a lot of time on this chart. Is this the laser pointer? Yeah. But what really jumps at me is that orange word deaths. And when you see that, and it's next to that blue line, and it's going way up high, and you say, oh my goodness, this is terrible. But it turns out that's actually vehicles, miles traveled. And one of the other increasing one is population. And if you go to the very bottom line about deaths per billions of vehicle miles traveled, there's been really improvements, and I think a lot of the safety factors that you had mentioned with I'm going to get a new car this fall, and I'm going to get everything I can on it because it's amazing what they've got out there. So there has been big improvements, but there can be better. So if I look at the basic problem for one autonomous vehicle, basically all you have is you have instantaneous sensor data and you have whatever a priori or map data that you have ahead of time. That's all you have. And from that, again, in every instant, you have to get your throttle, steering, braking, what do you want to get to come out of it. And for the instantaneous sensor data, one is localization. Can you get some idea, like a typical GPS might be, 4-meter accuracy, and it's not too bad. We can do better than that with some other technologies. Identify static objects, the terrain, where is it smooth, where are the curbs, and lane markings. But the moving objects are the big one, the other vehicles and pedestrians and things like that. How do we do it? And the main sensors that are out there, I think I just hit the accelerator pedal. I've got to go a little faster. The main sensors that are out there, LiDAR is very popular. So you shoot the laser and you get a point cloud. You get this point data. And the advantage is 80 meters is easy. We've got one sensor that claims iSafe 300 meters that we used in that mentioned about the Urban Challenge. That's the City Street DARPA competition I forgot to talk about. But you might miss the target. The beams, it's not continuous. Reflections due to rain, things like that, or certain materials don't reflect the material, the beam that well. Vision is great because it's passive. You're not sending any signal out there. But again, lighting and weather conditions and something as simple as the stripe in the road going under a shadow of a tree can cause some issues sometimes. Ultrasonics, when we started way back with some of our Air Force work, we were moving very slow. It was construction equipment, and ultrasonics is the poor person's sensor. They are inexpensive, but short range, and all you know is that in this cone of area, there's something out there, but you're not sure where. And radar is probably one of the best as far as bad weather and things, so that you can get it out there. But again, it's not pinpoint, sort of like a laser beam as far as locating where something is out there. This is our Urban Challenge vehicle. So that was the competition DARPA did out at Air Force Base that was closed in Victorville, California. You had to drive on city streets. Again, there was a $2 million prize, but it was a bit more subjective this time. Instead of who did the 150 miles the fastest, it was clear who the winner is this time. So first place was Carnegie Mellon, got $2 million. Stanford got $1 million, second place. Virginia Tech third, got $500,000 prize. If I was to ride in one of the vehicles, maybe I shouldn't say which one I would want to ride in. Ours is our vehicle. It's a Toyota Highlander that we did. We have a lot of single beam LiDARs down at bumper level. You see the SICK, but it's a German sensor, pronounce it ZIC. I don't know. So it sends out a single beam. So on the bumper level, there's sort of a plane of beams that are out there. And if you look at this top-down view, there's an L shape right in the middle. It has a number 36 next to it. That's what, from the top view, that's another vehicle. So we've got to interpret that as a vehicle. Some of the other objects, you see how we've grouped them together anyway, are buildings and things, and the vehicle itself is that rectangle that's not labeled in the middle. And then as you move forward, this is some of the technology where the prices have come down now. This is a Velodyne 16-beam LiDAR that we use quite regularly. And you can see how it's angled on the left-hand picture so that it swings the 16 beams 360 degrees. On the left of the blue dot thing, all that mess up there are the trees, because it's the back side of the LiDAR is shooting up there. But on the right-hand side, you can see the 16 beams as they're sweeping across the road. So again, you don't get continuous total data, but you get all these points as indicated by those blue dots. This is the 16-beam LiDAR that we put on our vehicles. We're driving around campus. So again, you get a lot of information. And the problem becomes how to interpret that fast. And the 64-beam LiDARs are very popular. When these first came out, though, I think the 64 matched to the price. I think it was $64,000. Yeah. So, but you get a lot of data. And you say, well, why is that important? Well, we're going to get to that. I forgot this slide. What about the a priori information? Okay, I got 5 minutes. Right, we're going to have maps. So how are we going to represent those maps? Are they going to be point clouds? Or are they just going to be, well, let's show the options. This is the map that we had for the DARPA Urban Challenge. It was a text file. And if you look down the list here, you see about halfway down on the left, it says number of lanes 2. And then 2 lines below that, it says lane 1.1, number of waypoints 4. And down at the bottom of the left-hand column, you can see 4 pairs of numbers. Those are latitude, longitude of certain points. And then it says end of lane 1. And then in the right-hand column, lane 1.2, so it's segment 1, lane 2, has 6 waypoints, and you can see the lat long. And the third line in the right column, no, fifth line, it says exit 1.2.4 and then 3.1.1. That means that you can exit or you can transition from segment 1, lane 2.4 to segment 3, lane 1.1. So that was our world. That's all we had. And from that, then, we would plan routes to, we were given a mission file, say go to points 8, 11, 20, in a certain order. So you had to plan your route with that information. So do you have a map like that, or do you give an entire point cloud? So this was us driving down one of the roadways in Gainesville with the 16-beam LiDAR on just one single pass, and you can even see the wires and the power lines, and it's a lot of information, but it's all available. Or do you take all that information and try to condense it down so you can make a voxel representation, so it's sort of like Minecraft representation. So on the left, you see all these boxes. And on the right, we did some classification. This is something for the Air Force. We were looking for tree trunks and not people. And the purple we identified as tree trunks out of the one image. So if you have the instantaneous sensor data and you have some type of map data, how do you decide what to do? I'm not going to dwell on this slide, but one of the biggest things we did on our Urban Challenge vehicle was how do you decide what behavior to do? Again, it was to go from that sense data, which is the blue thing on the bottom, to throttle, braking, and I'm going to zoom through that one. Okay. What can you get today? And I have to apologize to some of the other vendors. This is a Tesla video, but General Motors has some great stuff. A lot of the people have great stuff. So if you go to the showroom today and buy something, you can basically be on like an interstate and do lane changes, stay in your lane, stay behind a vehicle. Summon is kind of cute, it tells it to pull out of the garage and come get ready to go. And, automatic parking is, it's been out there quite a while. And the last one is emergency braking. And they're really good things. And I'd love to have that in my car, but it's not an autonomous car. So, again, trying to rush through in 15 minutes, then you go from what's available to buy today, go to some of the technical topics, maybe some of the things that keep us up at night. And I'm going to go back to the LiDAR. So the problem with the LiDAR is how do I take, for example, this point cloud? So on the left are all the points that were hit. I believe there's 16 beams here. Somebody was about 2.5 meters away. You get a lot of data. And you can see on the right-hand side, you can hardly see the dots at 17 meters. And 17 meters isn't that far, that you don't get that many hits. So how do I identify that as a person? So this is from a TED Talk from Chris Urmson from Waymo. One of the approach was they generated all these not scenarios, but data of actual people and have stored them, and then you compare, the point cloud little bit that you have to the models you have and identify. And then this is one of, I just wanted to show a case. I don't want to say things that keep us up at night, but let's see if I can get this to play. Play. Okay, it was playing. There's an intersection indicated by those orange lines, and the mouse was wiggling by a person there. And this is the raw data. And we've classified it now. There's the person, and the person's about to walk across the road. And you can see we're getting great point hits. The sensor is located at the intersection of the blue, green, red lines. And as they walk across the road, look at how it disappeared. Now, if you look at the raw data, there's still data there, but our algorithm said there wasn't enough points to classify that as a person. So that's a problem. And it's not a problem that's going to go away. Now, on Tuesday, the student ran in, hey, I got a new video. I've got that case solved. And I didn't bother to put it in the presentation. Because we'll have a new problem tomorrow anyway. So, but those are the kinds of things that cause trouble to get out of there. So I'm going to go to issues. A lot of you say it has to work 100% of the time. Nothing works 100% of the time, but that's not the real issue. Oh boy, I got 40 seconds. When the system realizes that it's having trouble, it has to be able to turn over to the human, in enough time, things like that. So the whole system has to work 100% of the time, let me put it that way. I worry about, maybe this is what I should have said, the stuff I worry about: sensor performance, poor environmental conditions, false positive, negatives. This is one I think Dr. Clausen's going to talk about, is things like this. if I'm in the vehicle, do I want the vehicle to explain to me what it's doing? I feel better if I see this map and I see little boxes around the other vehicles, that it's identified them, and I'll feel better. I'm not grabbing the wheel, though. And then the communication issue, I think that's going to be a really big plus, vehicle to vehicle, legal, ethical issues. And so what I'm going to end on is I got two videos, and I think this is from Vietnam. So I call it the intersection of the present. And some of this guy here. So, but nobody is, maybe it's efficient. They're all moving. Nobody is stuck. So we go from that, and I found this. It's at low resolution, and it was the reference. It was from France, but here we go. They put a lot of time into this, I believe. So. And it goes on for a little bit longer. So that's definitely not what Gainesville looks like today. So thank you for your patience. Again, try to give a sort of a quick shotgun overview of the technologies that are out there. And we're going to turn over to Dr. Clausen now for the next.
So, after all of that, I feel very compelled to represent and to present the human perspective, to be able to see how folks are experiencing all of these exciting but also challenging times as we are really standing in the transportation revolution. I'm an occupational therapist, so what OTs are doing is we are interested in the person, the vehicle, and the occupation, or those meaningful tasks that each one of us have to do to be able to survive, to strive, to thrive, to live meaningful lives, and of course to drive. So from that perspective, I'm going to talk about a study that we've conducted at the University of Florida to look at older adults' perceptions of autonomous vehicles. So I'm going to use the scientific outline to be able to frame my presentation. So it's going to be a true scientific presentation and a little bit of background in terms of older drivers or older adults. So we know that the demographic shift in America is happening, and about 20% of the US population is over the age of 65, and that is to increase in the next 10 years so that we will have 1 out of 4 drivers will be over the age of 65. Despite the fact that older drivers have issues with medical issues, declines as a result of the normal aging process in their cognitive, their visual, their motor, and their sensory functions, as well as being on complex medication regimes, they are, and that causes that they are at a higher risk for crash-related injuries and fatalities. Despite that, driving is still the preferred mode of transportation among this population. So autonomous vehicles may hold excellent opportunities for these drivers to offset some of the health as well as the safety issues. Recent perceptions were measured by survey only. When older adults were asked about autonomous vehicles, survey only. So we thought, well, if we can use the surveys, but if we can also expose older adults to some of these autonomous vehicle technologies, what will we see? And the expectation that we had going into this study was that their attitudes, their perceptions, their values, and even maybe their early adoption thoughts may improve as a result of exposing them to some of these technologies. So what we did is we exposed them to a driving simulator that was programmed at the SAE level 4, and we also exposed them to the autonomous shuttle, the one that Dr. Lilly showed in the previous presentation. So obviously, because we are working with human subjects, we had to go through ethics approval and received a full IRB approval. That's the Institutional Review Board approval from the University of Florida. And we developed a repeated measures crossover design, and I'll say a little bit more about that in a second. We recruited the participants from the North Central Florida area, but with a concentration in Gainesville. And we included folks if they were at or older than 65 years of age, and if they had valid driver's licenses. And the exclusion criteria pertain to their performance on the Montreal assessment, cognitive assessment, and using the indicators of that particular assessment to understand cognition and cognitive declines. We had a variety of measures that we used, and I'm not going to go over all of them, but on the left-hand side you can see some of them pertain to clinical tests looking at set shifting as well as user perception surveys. And then also the driving habits questionnaire, which basically calculates or describes older drivers' habits, and the life space questionnaire that help us to understand how older people are moving in their home, outside of their home, in their neighborhoods, or do they even cross state lines as well. So, let me just go back to this one. On the right-hand side, you see the RTI, High Fidelity Driving Simulator. So in this simulator, it's got a full car cab, and the older driver would sit behind the wheel with a research assistant in the passenger seat. There's life-size images that's been projected on the actual screen. And folks, all the experiences are a very immersive experience with very high, what we call physical and emotional fidelity, meaning that the believability of this situation is really high. On the bottom is the TransDev Easy Mile Easy 10 autonomous shuttle that's also been programmed at the level 4 of the SAE standards, and that's the shuttle that we've used. In this particular shuttle, we had 6 older adults at a time in the shuttle, and we had a research assistant as well as the safety operator accompanying the older drivers. And because of the not having the actual NHTSA waiver to run the shuttle on the public roads, we conducted this study in a bus depot in Gainesville. So after folks enrolled in the study, they completed all of the baseline measurements that I've mentioned in the previous slide in Visit 1. And then they were randomly allocated to Group 1 and Group 2 because of the crossover design. So for folks in Group 1, they were first exposed to the simulator, and then they were exposed to the shuttle. And after each one of these exposures, we actually used the AV user perception survey to look at their perceptions prior to exposure, exposure after the simulator, and exposure after the shuttle to see if there's any changes. And then Group 2, we flipped the order of the exposure, and they were exposed to the shuttle first and then the driving simulator. So we collected the data by trained research assistants, and we entered that in a REDCap system that adheres to all of the privacy and the confidentiality policies at the University of Florida. And our analysis was conducted with statistical software, SPSS version 25. And today I'm going to give you a preliminary look into the data that we found. We haven't completed the study yet. We are enrolling 105 older adults, and this is 69 older adults that's completed the study. So please see this as preliminary data, and of course we cannot make any causal conclusions as a result of that. I just want to say something about the user perception survey. When we started the study, there were no user perception surveys that actually asked the questions that we wanted folks to answer. So we had to design our own user perception survey. So this is still undergoing psychometric testing, and so it's in development as well. But some of the things that I would like to highlight is that we basically have 28 questions on the table over here. Oops, the pointer is not working, but you can see that there's a total of 32 questions. 28 of them are all questions pertaining to perceptions, values, beliefs, and experiences with autonomous vehicle technology. And then we ask 4 open-ended questions, so such as the disadvantages or the advantages of autonomous vehicles. So all of these items derive from basically the dimensions, which is in the top left-hand corner. So we look at questions pertaining to trust, safety, control, experience, etc. And all of those dimensions are basically conceptually embedded in some of the existing models. That's at the bottom. There are 7 existing models. So as I say, psychometric testing is continuing with this particular survey, but this is the survey that we use for this study. So if we are looking at the results, so this is some of the demographics of our participants. So for shuttle first exposure, we had 20 women and 18 men, and the women were a little bit younger than the men in comparison. So 73 was the mean age, 77 the mean age of the men, and that pattern pretty much held for folks who were exposed to the simulator first as well. If we look at the gender distribution, we had so far 29 men, that's 42% of the sample, and 58% female, and that's a pretty good representation of the current demographics for gender according to the Florida census statistics. In Florida, it's 45% male and 55% female. If we look at racial distribution, so we had 87% of the folks that self-classified as Caucasian or white, 9% classified as black, and 4% classified as other. This is an interesting slide in terms of the actual education. So Gainesville being a college town, and much of our recruitment occurred amongst the older adults in Gainesville, you can see that 73% of our participants had either bachelor's degrees, master's degrees, or doctorate degrees. So that is totally, of course, skewed in terms of the general population. We also had 23% of our participants having a technical school, some college, or an associate degree, and 4% of our participants had a high school diploma or a GED. So a little bit skewed in terms of education, so we worked with a very highly educated group in the study so far. Right, so I'm going to show you the results of the entire group before the actual exposure to any of the technology and then exposure to the shuttle and the simulator. So a brief orientation here is that on the y-axis you will see the user perceptions, and we measured that with what we call a visual analog scale. And so that's a scale that is numbered from 1 to 10. It's exactly 100 millimeters, and we use that as numeric data to be able to measure the perceptions of older adults. And on the x-axis, we have the baseline condition, the shuttle condition, as well as the simulator condition. Thanks, Lily. So the variables on the right-hand side pertains to the social influence, the intention to use, and the cost. And all of these, if the graph is going up, it shows that older adults are more favorable to each one of those conditions. So you can see that was the case for being exposed in the shuttle as well as in the simulator, although there was a dip when folks were exposed to the simulator. The outlier here is the intention to use, where the older adults were really more positive after they've been exposed to the simulator, and the intention is, of course, to use autonomous vehicle technology. For the actual next three variables, this is pertaining to how media influence people, as well as their trust of autonomous vehicle technology, and the controls. Do they want to take control over of the vehicle, or would they rely on autonomous vehicle technology? You can see that the graphs are pretty much telling us the same picture. At baseline, they are lower. Once they get exposed to the autonomous shuttle, sharp increases, and then to the simulator, we see that the graph is decreasing again. And then our last four variables pertains to authority. That's pertaining to trusting the National Highway Traffic Safety Administration's safety measures, perceived usefulness, perceived ease of use, as well as safety. And in each one of those cases, again, you can see that folks felt much more positive to these four variables after they've been exposed to the shuttle versus being exposed to the simulator, but still the simulator had an effect. So if we then looked at what happened in the groups, so if we look at group 1, you will see that they were first exposed to the simulator and then to the shuttle. Now, I don't want to be saying that we can make causal inferences, but we did look at statistical significance, and that's outlined in the red font over there. And we also looked at effect sizes to tell us how big the effect is. And what we learned from this first table on the left-hand side is that the older adults' trust increased quite a bit after they've been exposed to the shuttle last, as well as their perceptions of safety after they've been exposed to the shuttle last. And then for group 2, where they've been exposed to the shuttle first and then the simulator, we see that the intention to use increased. So we think it's because in the simulator they were sitting behind the steering wheel. It felt like they were an operator of the simulator, whereas in the shuttle they were more passive as a passenger. Okay, so my take-home messages, overall analysis, exposure to AV technology positively affects older adults' perceptions to this emerging technology. Perceived safety shows the highest percentage points of increase after being exposed to the autonomous shuttle, and then intention to use shows the highest increases after being exposed to the autonomous shuttle. To the simulator. The within-group analysis showed us that trust and safety significantly increased if they were exposed to the autonomous shuttle last, and intention to use significantly increased after being exposed to the simulator. So our next steps is then to do, of course, to complete the study and to look at gender and age and time effects as folks are being exposed to this technology. This is also laying the foundation for us to further look at folks who are disabled, those with dementia, the disadvantaged, the de-skilled, as well as those with degenerative diseases such as the degenerative neurological disease. Because we do believe that transportation, like Mr. Leonard had said, do not just need to be affordable, effective, integrated, and ubiquitous, but for these special populations, it also needs to be accessible, acceptable, adaptable, and available. And so, we hope to further the work in that area. So I want to acknowledge our funders as well as our stakeholders, and then each one of the project team members, specifically Justin Mason, our postdoc, Dr. James Versell, who did much of the data collection, Virginia CCO Pico, one of our collaborators, Jason Rogers, and our research assistants, Melissa Varera and Casey Clark. So thank you so much for your attention.
So I think we are slightly ahead of schedule, right? So maybe I can take a few more minutes. All right, let's just make sure. All right. Good morning. I'm Sanjay Ranka. I'm a professor in computer science. I do mostly artificial intelligence for transportation and healthcare. So what I'm going to talk about today is the world is changing, where in the past, most of the data in transportation was collected by the government or third parties like Google. But now with autonomous cars, all the car companies are going to also be having data, and that's a new player in the market. And the key goal is to be able to create a symbiotic relationship. And in my mind, the way to do that is make things more real time, because at some juncture, all the cars which are driving around, they have to interact with pedestrians and other vehicles. And the more real time information which you can provide to them, the more amenable they are going to be able to use it. And obviously, that's going to improve both safety and operations. What we are trying to do is we're trying to build a data store, again, try to be able to access that in real time, to be able to achieve a variety of applications, both from monitoring, from evaluation and analysis, be able to do predictive modeling, be able to do optimization of a variety of issues in signal and corridors, and also support planning and investments. Again, the key goal obviously is to both manage traffic congestion and improve safety, but make everything data driven. And also be able to support efficient movement of goods, services, and people. With that challenge, I'm going to talk about some of the projects which we are working on trying to make the infrastructure smarter and more real time. The goal is, at a very high level, to be able to compute everything on the edge, as they call it, right near the signal, as close to the signal as possible, because you want to make it real time, and then be able to assimilate key findings and push that to a centralized environment like a cloud, so that you can do more longer term analysis there. Clearly, the important part here is to be able to be resource efficient and be able to use a variety of sensors which are available to you today and which will be available to you in the future, and that's what we are working towards. So one of the projects which we are working on is what I call smart intersections. So the idea basically is that you have an intersection, typical intersection in any city, which has loop controller data today. There are loop controllers under the roads, which give you data about every vehicle arrival. You want to be able to use other cameras, like video cameras, which are called fisheye cameras, sitting on top of the intersection, and in the long term be able to use LiDARs and other sensors to be able to collect information in real time about all that's happening on the intersection, store it in a sensible form, keeping track, making sure that we obviously worry about privacy issues, and then be able to understand what's going on at the intersection in terms of anomalous behavior or in terms of near misses, to be able to provide feedback to planners as well as architects of intersections on what designs actually are more effective and what signal timing plans actually are more effective to improve both operations and safety. So what we're trying to do is we're trying to develop these real-time scalable systems which can actually collect data from loop controllers as well as from video. First, I'll talk a little bit about the loop controller part of it, and then I'll talk about the video analysis. To be able to collect the data in real time, to be able to run all these algorithms for detection and everything else in real time, and be able to then push that information back to the autonomous vehicles in real time for this to be effective. So we are developing this system for understanding what's happening at the intersection, both at an intersection level and as well as at a city level. We work both with the city of Orlando and city of Gainesville, collect information from all the signals which they have data for to be able to analyze it. And I'll show you some of the results from a broader perspective and then go back to the intersection level. So for example, in this particular case, we can actually process 1 week of data in less than an hour. And that's our goal. Our goal is to make everything as real time as possible so that the information which is gathered is captured and processed and analyzed and sent back to the vehicles and the pedestrians. We can actually take all the data in a given city, rank all the intersections in terms of their performance so that traffic engineers can understand what's going on at every intersection and get a broader picture of. I'll give you an example of this, where essentially what it will do is it'll rate, if you look at 1, it shows the different categories of intersections, whether detectors are not working properly, or they have capacity issues, or there are timing issues. Again, the intent basically is to provide a traffic engineer with a good perspective of what's going on in the entire city so that they can make changes in real time in some cases, or at least at a daily basis. So they can select all the information about what's going on in the city for any given day, be able to figure out the weekday versus weekend behavior, to say, hey, this is where my problems are during the weekdays and the weekends, understand what's happening in the morning, what's happening in the evening, so they can plan the traffic signal timings better. Again, the goal is to make the infrastructure smarter so that they can interact better with the traditional and autonomous vehicles. So this one kind of shows you that the behavior changes by the hour and how do you plan for that. Also, be able to do a change detection automatically to say where the change is happening so you can focus on those changes. This kind of gives you an idea in terms of a broader infrastructure. What I'm going to now talk a little bit about is how do we do real-time video analysis to be able to understand what's happening at an intersection and again be able to generate messages on the fly and be able to support in a few years information to the autonomous vehicles about what information is useful for them, what's happening in the city, if there's for whatever reason there's an incident, and at another intersection, can they change their route dynamically? So this one kind of shows you, again, real-time processing of an intersection in Gainesville, where traffic is coming. We're tracking different kinds of objects. In this particular case, I'm showing you in real time all the cars. The greens are a bike or a motorbike, and the yellow is pedestrian. So all this tracking is happening in real time. Also, this kind of gives us a good synopsis of what's happening at the intersection. We collect this data in real time and then process it to understand behavior. You see this video is playing again and again. What this does is it gives us information about all the vehicle trajectories on that particular intersection. So these are color coded for different directions. The light, all the trajectories are marked so that the light ones where they start and the dark ones where they end. And this shows you the behavior at that particular intersection. Again, the goal is to be able to analyze this and be able to rate all the intersections in terms of their safety and operational quality. This shows you the behavior on the right-hand side based on different phases. Generally, every signal has 6 to 8 phases, and each phase has different traffic behavior. In some cases, people are going east-west. Some cases, people are going north-south. And then be able to also understand what's happening on a given phase, because traffic sometimes moves in a fashion that two directions can interact with each other. So we can actually show that. We actually then are able to analyze also all the pedestrian trajectories on the intersection. So see how many people are actually jaywalking on the intersection, how many people are not following the paths. And again, we can do this for morning times, evening times. The other interesting part which we do is we look at anomalous behaviors, right? So for example, these are all the trajectories here which show you the vehicles which are crossing on the red light in a given hour. The key goal of all this is that once I can analyze this data, we are able to then predict behavior and then be able to use that for better intersection design. And in some cases, then the end goal is to, if you look at the left, there's a pedestrian crossing the traffic and goes back, right? So we want to be able to capture that kind of behavior and be able to warn all the traffic on that intersection to say, hey, there's a pedestrian crossing where they should not be crossing, be aware of it. So these kind of real-time messaging and real-time processing is very important to improve the safety in the long term. And the goal is that any object which can actually communicate at the intersection should be able to get that piece of information. Here's another example. If you look at the behavior of this particular pedestrian, they come there, there's a red light, doesn't want to wait, comes back and J crosses. So we want to be able to track all this behavior in real time and be able to send this information to all the vehicles on the intersection. We also want to be able to detect near misses. So if two vehicles are coming very close to each other, we want to be able to say, hey, there's a potential problem there. And the key challenge, of course, there is that we're dealing with spherical cameras which have distortion of all kinds. They see better near and they don't see very well far away. We have to be able to take care of that. And then again, be able to find out. So here's an example. On the top, if you see there, that vehicle suddenly stopped in the front. So the vehicle behind braked. And if it didn't brake, there would probably be a crash. And the vehicle possibly braked in this particular case because there was actually a fire truck behind, which was beeping. So the vehicle in the front stopped in the middle of the intersection, and the one behind went further. Another example of that, if you look at these two vehicles, they come very close to each other, but that's normal behavior because they're just passing each other in different directions. They came very close to each other, but they're in different directions, and that's not really a near miss. So we have to be able to detect both things which are real misses versus quote unquote the false misses, if you may. So we do this analysis by collecting the data in real time, and then part of our project, Lily mentioned this, to be able to do this in the trapezium project, where we will have all these video cameras at 10 out of these 23 intersections. We'll collect the data and be able to essentially share the data with the smart and connected vehicles in real time about what's going on in the entire network. Be able to analyze the network itself, detect all the incidents which are happening on different parts of the network, and relay that back to autonomous vehicles, and be able to optimize at the network level. We also do other work on the infrastructure side, where we understand by looking at vehicles which are passing on highways to be able to say what commodity are they carrying. One of the interesting parts of understanding behavior on highways is to understand how commodities are getting transferred in the state of Florida, and obviously this can be extended to the entire nation by essentially looking at the type of object and logo detection of what company it is. So if it's Walmart, we know what kind of goods they are carrying. If it's FedEx, we know what kind of goods they are carrying. So we can understand in real time how goods and services move around in terms of freight planning and everything else. The other thing which we do is we look at highway videos to understand how vehicles enter and exit ramps. How does that impact speed of the different vehicles which are coming in? To be able to then understand what kind of ramp changes need to be made, or what kind of designs are better than other ones to be able to be effective. This is my team. There are 4 faculty involved in this project and 8 or 9 PhD students. We effectively develop a variety of these techniques. I'll leave it, our work is supported by NSF Smart Cities Project and FDOT. I'd like to acknowledge them. Also, this is a McKinsey study which showed the importance of different levers in terms of improving transportation. It just came out 6 months ago. And UFTI as a whole is focusing on the top 5 there, which can actually have a real impact in terms of improving traffic performance. Thank you.
Thank you. Do we have a few minutes for questions, I believe? Oops. Yes, please.
Thank you for visiting us. We're an academic institution, so we'll give academic reactions to what you've said. I'll give you 4 quick ones. For your presentation, what you've discussed about improvements in autonomous vehicles at intersections could be done now. Nothing preventing that from happening now. So it would be useful to think a little bit about the political economy of why is it we aren't doing these things now, and we're going to need autonomous vehicles to get them done. I'm not saying you answer it, but it might help to sort of motivate what's going on. I'll go quickly through the 3 other ones, and these are largely for motivation. On your presentation, you show the sort of stylized facts about the declines in fatalities per VMT. True, nothing obviously to dispute about that. The issue is why. We're really not so sure about that. I mean, one can speculate about improvements in vehicles, but it's very hard to show that kind of thing. I would suggest that an equally compelling explanation is the increase in congestion that's occurred at the same time because people are going slower, simple physics. Point being, that's a benevolent way to reduce traffic fatalities, is congestion. And the point that I would make is that we're sort of running out of good ways to save lives, and that's where autonomous vehicles comes in, because that's going to be able to accelerate the decline, and that's a good thing that's going to happen. On yours, you didn't have time probably to go into detail, but it'll help to know more about the people in your sample. In other words, what was their accident experience? Have any of these people been in accidents? Do they know people who've been in accidents? How much VMT they drive every year? They care about safety in the vehicles they buy. Going into this, this would be an interesting comparison. Are there groups of people who we think, because of their own experience, vehicles, and so on and so forth, are going to be open to the benefits of autonomous vehicles and safety as compared with others who aren't at all similar to those experiences, will obviously be very hesitant to believe that for a variety of reasons. It might be interesting to sort of point all that out.
I'll comment on that by just saying that we do have that data, and so that will be analyzed as we are done with the entire year.
Yeah, that'll be important, I think, in terms of the people who resist it. And on yours, I think the thing I'm thinking is long run. is the road network going to change because of autonomous vehicles? Remember, we have built this network based on non-autonomous vehicles. And I'm seeing all these intersections and I'm thinking, yeah, well, we had that because people couldn't get close to their destination and they got to walk across city streets. So maybe traffic patterns will change. Maybe we'll realize, these kinds of intersections are bad, roundabouts are better, or for that matter, we don't even want these kinds of things. It doesn't hurt to start treating now the changes in the network that will come about because of autonomous vehicles and start speculating. Obviously, you can't do any of this now, but I think that we're going to learn a lot as we go into this, and we're going to see both pedestrians and the network changing. So those are suggestions to help you.
Okay, thank you. Yeah, with respect to your question, if I got it right, yes, we can start doing this now. One of the issues is the chicken and the egg. The vehicles need to be instrumented. The infrastructure needs to be instrumented in order to communicate. I think that's what is unique with what's happening in Florida is that both are happening at the same time, and that allows us to start getting those benefits. Carl?
Just going to say about the, I have to hit a button, about the congestion. That's a very good point.
Oh.
Push and hold, or
There we go. That's good.
how about now? Anything?
Yes.
Okay.
Yes.
All I want to say about the congestion was that's a very good point that I hadn't thought of, but it's definitely not what I want to see happen. But that's an excellent
Yeah.
point. Yeah.
Quick comment. The infrastructure unfortunately doesn't change overnight, right? So all these highways and road networks are built over decades. So I know that these things are going to stay for a long time. We have to work with whatever we got right now. And of course, as we learn more, as you're pointing out, they will evolve, but probably take several decades before that happens.
Any more questions? Yes. Mike's coming.
Thank you.
Yes.
I don't know. Okay. Urban planner, it strikes me this is fascinating. And the big data revolution is giving us tremendous resources. But where do we draw the line between rational human behavior and irrational human behavior? Because theoretically and totally unacceptably, you can have, collect the entire, data on the entire history of one pedestrian who is apparently trying to cross the road. The mental history. Is he out of an institution? Might he have a relapse? Does he have something in the family recently? Yeah, we have the data about that. Yeah, his wife is behaving. Where do we draw the data? Where is the human responsibility in that? And not ours and yours as scientists, but ours as individuals. Thank you.
I think one of the points Sanjay was making was the real-time information and warning, and so being able to recognize or predict intent that's I think where that technology can be very useful. Okay, more questions?
But just to add to what Lily just said, the doctor can only tell you what you need is good for your health. If you still want to do stuff which is bad for you, at some juncture, we can only prevent other people from not getting impacted.
Yeah. Over there.
Thank you. I just saw an article online where the Attorney General is ordering that software always be created with a back door so that government can access it. Of course, wherever there's a back door in technology, hackers can misuse it. What are the provisions for encryption security in autonomous vehicles? Will they have no back doors so that no hackers can intrude? And to follow up on the previous gentleman's point, we probably all remember the Geico commercial where the squirrels are like high-fiving each other for tricking a car and running off the road. What happens when 15-year-old kids see autonomous vehicles coming along, decide to kick a soccer ball across the street and watch what happens?
Yeah, on the second part, I think that's already happening, and these are just anecdotal stories that I've read online, but people challenge the autonomous vehicle. They'll drive right in front of it because they want to see what it does, and that's a problem. The encryption part, I'm probably gonna have to pass to Sanjay myself, because the level that I've been at is just got to get it to work, and that's becomes kind of my secondary concern. But boy, if it is hacked into, it could just be chaos. I don't know. Do you have any comments to add?
Yeah, I don't really know much about the security of autonomous cars themselves, but on the infrastructure side, we are making sure that whatever we actually collect, we throw away as soon as possible. So we don't, like for example, the video part which I talked about, we just need it for 5 seconds, and after that we process it, and at that juncture, the video is useless for us. We just want to get the meta information about what's going on. We obviously are very careful about privacy issues, and we encrypt all the information which we keep. We anonymize it, that even if you were able to get to it, it's useless for you. Because our goal is not to track people, our goal is to understand behavior.
Yes, there was over there.
Thank you. My question is about the connected infrastructure and the infrastructure pieces. Because I know in the autonomous vehicle community, there's an actual competing theory, including one that's being tested right now in Florida at the villages, where they want to be completely independent. They don't want this connection. They don't want to have to depend on the infrastructure being there, doing what it's supposed to. They want the vehicle to be smart enough and the mapping to be good enough. So I want to sort of talk to you about, get your take on what this debate is about connection versus true autonomy.
Yeah, this is a very interesting, I guess, competing approaches. And in my view, you need to have both to maximize safety and to avoid making congestion worse. I don't think it can be done without the connectivity, just purely with autonomy. The information that you can get with connectivity supplements very nicely what autonomy is able to do. So in my view, the two have to work together.
Yeah, I was gonna say, when it all started, like 2007 was the urban challenge, and you didn't want to rely on anybody. It had to just be you. And part of that, though, is look at the impact cost of the infrastructure. So we had no impact on the infrastructure, and yet you could get it to go. But the benefits are, if there's other vehicles, especially pedestrians, this is one of the projects we're doing now, is that if I can be told that from sensors at the intersection or from other vehicles or whatever, that information is just really going to help me. So again, when we started, well, there is nothing, so we're just going with the current infrastructure. But I think anything that's added is just really going to be a benefit. So.
Yeah. Okay. Yes.
So a good segue for my question is, so if these autonomous vehicles are relying on the connected infrastructure, and as we all know that things break at one point in time, where is the line that you will draw in terms of how autonomous systems are supposed to be just self-sufficient, right? Because otherwise, people will start taking shortcuts and build systems relying on the infrastructure that may fail and may create some potential hazard.
I was just going to offer my opinion is I think it ought to be self-sufficient, and anything I get in from any other source is a bonus for me. It's going to make me better. But I think it's going to have to be. And as it all develops, too, I mean, we're in north central Florida, and you don't have to go very far to be out to not much infrastructure. Well, I don't want to take that back. To, minimal things. And I think the self-sufficiency is going to have to be with us for a while.
So by definition, most autonomous systems are fail-safe. That means they will work independently, maybe at a lower quality than expected if the information is not there. And the goal is that they become more efficient as more information is available. But the intent always is that things should work even if everything else fails.
Yeah, I think there has to be redundancy. I also think that deployment will be facilitated if both work together to supplement the information that the autonomous vehicle has right now. For the examples that I showed, for example, where you don't have line of sight to obstacles, but having information from the infrastructure allows you to get that. Okay, over there.
Yeah, I'm sorry I was late. Maybe you covered this. Thank you. But I was wondering about a time frame. A lot of people say this is going to happen much later than what we think. And maybe this is another group, but supposedly the 5G network is very important, and China's way ahead of us, and we're arguing with Huawei, and are we going to use them or not use them? Supposedly it'll be a security risk. And so I was and also trucks. Now those are high-paying jobs, truck drivers. Are you just doing vehicles now, or will they be doing trucks later? Is one? I've heard that there'll be one lead-in truck with one person and then autonomous behind it. And I'm wondering if a young person, not I, but if young people want to get into this field, what's their best major in college, or what should they be studying?
Well, I just tell our students that the whole area is, and the last part is a mix of mechanical, electrical, computer science, and that you can major in any of those, but you're going to learn about all of those. Mm-hmm. So it's a blend. Maybe it needs to be a new major. I don't know, but
traditionally the transportation systems has been under civil engineering, but you see here the collaboration that happens at the research level, and we want to bring that also for the students. So we have transportation across different colleges, across different departments, and it becomes so much more important now with advanced technologies at the forefront.
it's funny, you go to different, electrical engineers are going to say it's all electrical. They're number one, and the computer person.
I would say that the world is changing, where you could take one profession and work there for 35 years and you retire. I told my 2 daughters, just learn how to learn, and after that you'll be fine.
Yeah. All right, we are officially out of time. I put up takeaways from this session, from the different presentations, and we welcome more discussion. Thank you very much.
Thanks for watching. Be sure to like and subscribe for more videos from Brookings.